Hey, welcome back, everybody. Hope everyone's doing okay. Any questions? Questions, comments, concerns? A quick note, a reminder about Canvas. Canvas, the tech support people strongly suggest that you utilize Chrome. That's the best browser. And well, it's the best browser, but it's not 100%. And so if you ever get a question and you don't see the image, please let me know what the question is. For some reason, Canvas has a challenge of showing images, and it varies from person to person. It's not like it's everybody. It's just occasionally this person for this homework or this assignment can't see this image. We can't nail it down. But so in that case, so if anything like that happens, let me know the assignment, the question, and we'll look into it, and definitely we'll give you credit if that's the issue. Okay. All right. We were on chapter. Oh yeah. Question, Jacob, the nomenclature exam? Yes, by all means. The nomenclature exam. In fact, I've had a couple already attempted. One's already done. Remember that the nomenclature exam is per departmental rules. You need to get at least an 80%. That's 16 out of 20 questions. Nomenclature meaning naming, either you're given a formula, from the formula give the name of the compound, or from the name give the formula. Okay, and that's open throughout the semester. Not that you have unlimited, no time limit, as far as unlimited attempts, I should say. So do it as many times as you want, get to that 80%. I do go in there and I check some of the answers because, again, Canvas is learning. And for whatever reason, you may inadvertently, add a space, and Canvas doesn't recognize a simple space and counts it wrong. So I do go in there and I check, or you inadvertently maybe put a decimal point or something. So I do check it. We will get more information about, we have book chapter and nomenclature coming up. And so knock it out early if you like. Now, what effect does it have on your grade? It can have an effect if you're on the border, okay? And so what I do, and I won't do it now, about halfway through the semester, I would, if you hadn't reached that 80%, I would go in there and just input a 0. Now, why do I do that? That's to show you the effect of your grade, because Canvas right now, the grade you see is based on only graded material, okay? And so there's things out there that haven't been graded maybe, and so it doesn't really truly reflect your true grade. And that's what happens with nomenclature. And what happens, I've had in the past, is students have gone along through the semester and put it off and put the exam off, And then about 2 weeks or so before the semester ends, I actually put a 0 in there, and then they see the effect, and it actually pushes people down into a lower grade, and they're getting shocked. Now you only got 2 weeks or so to finish up. And so to eliminate that, I put a 0 in there if you haven't done it, or you haven't reached the 80% mark, to give you more reflect your true grade. So that way you know for sure there'll be no surprises at the end. Eduardo, you had a question about metalloids. No metalloids. It's either going to be what we call ionic compounds, we're going to learn about those, and covalent compounds, but no metalloids. Okay. Yes, we're going to just talk about metals and non-metals. That is correct. Yes. Yeah, if you move up in chemistry, you definitely will get into metalloids and so forth, but not here, not in general chemistry. It's going to be either metals or non-metals. And there's only 2 types of compounds we're going to learn. We just talked about metals and non-metals. Well, when they combine, a metal and a non-metal makes a specific type of compound, which we call ionic. You're familiar with that one. Next time you put on your French fries some little salt, sodium chloride, guess what? That is an ionic compound. It's a combination of sodium, which is metal, and the chloride, which is a nonmetal. Carbon dioxide, it is made up of carbon and oxygen, which is two nonmetals. Those are totally different type of compounds. We call those covalent compounds. All right, and we're going to learn a lot about that. So down the road here. Okay, good questions. Any other questions? All right, so let us continue with this chapter. Again, this chapter deals with conversion factors and so forth. Kind of introduce you to using this technique when we get down to chemical reactions, all right? Volume by displacement. Okay, now remember we talked about the units of milliliters for volume, either cubic centimeters, which is cm superscript 3, or cc, meaning cubic centimeters. Okay, that is the units for volume. Now, if we put in this example, if we put a diamond, or it could be anything, you know, into a cylinder, graduated cylinder, which is just a cylinder which has graduations on it, so you can measure the volume. And that thing, that graduated cylinder starts off with 20 milliliters of water. If we take this diamond or this object and we put it in the cylinder, obviously that object is going to displace the volume. So what happens? The volume goes up. It's analogous to the next time you're in the hot tub or in the bathtub. You know, that tub has X amount of volume. You jump in, what happens? Volume goes up. Your body, your volume displaces an equal amount of volume. So if you have a means of measuring that displacement, you can determine the volume of your body, okay? If you're completely immersed. So in this case, the volume goes up to 34.7. Now, the important aspect about this volume by displacement, the volume of this object, which is the diamond, is not 34.7 milliliters. That diamond is not that big, okay? So the displaced volume is the difference of the water that was displaced. So it starts off at 20 milliliters, it goes up to 34.7. The difference, 34.7 minus 20, is the actual volume of the diamond, okay? So in this case, excuse me, that volume displaces 14.7 milliliters, and that is the volume of the diamond. 34.7 is not the volume of that diamond, okay? Now that you have the volume, guess what? You can take that same diamond, weigh it. Now you got a mass, right? Mass over volume gives you density. So, all right, so as we stated before, diamond is made up of carbon, which is, very, when we think about the atom of the carbon, it's the same atom. I shouldn't say the same. It is the same atom, be it a diamond, or in your body made up of molecular structure. It's still carbon. It still has X amount of protons and neutrons and electrons. Okay, and yet the way it is configured, the way these atoms configure with each other, has big effect on the overall properties, specifically the diamond. The way it's configured makes it diamond a very, very tough material, one of the strongest materials on Earth. All right, volume by calculation. There's two ways to calculate volume. The first one we just talked about, displacement. And this is for objects that are irregular in shape. You simply can't do a simple get a ruler and measure length, width, and height, right? If I got a pair of scissors here, how do I get the volume of the scissors? Well, it's tough to do a length, width, and height. So what I do, I put this into a container with a known amount of volume, measure the displacement. Now I got the volume for this irregular shape. For materials that are regular shape that you can actually do a measurement, you can do a direct calculation of volume, which is the three dimensions, length, width, and height. And so to calculate the volume of a box, we simply multiply length, width, and height, okay? So in this case, we got 24 centimeter by 11 centimeter by 16 centimeter, okay? Note something here. Remember your sig figs. In this case, we did a subtraction. So we're not concerned about sig figs with respect to subtraction, okay? We're concerned about decimal places. And so 34.7 minus 20.0, they both numbers have one decimal place, so our answer should have no more than one decimal place. When we do a multiplication, okay, here we got to be concerned about sig figs. So we got 24 with 2 sig figs, 11 with 2 sig figs, 16 with 2 sig figs. So therefore, our answer should have no more than 2 sig figs, okay? So 24 times 11 times 16 equals 4,200. And don't forget your units, okay? Centimeters times centimeters is centimeters to the third power, okay? No different if I were to banana times banana equals banana squared times banana times is equal to banana cube times banana is equal to banana to the fourth power, etc. Okay, right. That's where your algebra comes into play. And again, not sophisticated matrix algebra, straightforward algebra. All right, so density. We had talked about density is amount of mass per given volume. We call the equation of mass divided by volume. Okay? So we're going to have two different units, mass normally in grams and volume normally in milliliters. Now you can do different units, but the point is the units for density would be a mass, be it grams, be it pounds, and a volume, be it milliliters or gallons, whatever the case may be. All right, so it will have the units of mass over volume. Now, the majority of the units that are utilized, the majority of the time, is the one in the middle, which is grams per milliliter, okay? Which is also equal to grams per cubic centimeter or grams over cc. The important aspect about this, it's a ratio. And as I talked about, any factory that we're going to be using this ratio of mass over volume, I can set that ratio up to either have mass over volume or invert it to have volume over mass. Which one we need depends on what we're going to do with it as far as mathematical calculations. Now, think of the density as how much matter is in a given space, okay? And so let's think about this for a second. All right, let's say we got a Hershey bar. This represents my Hershey bar. This is my phone, okay? Big Hershey bar. And so we all agree, we should agree that this Hershey bar, this dimension has an X amount of density. Why? I can measure the weight. So I got me a mass. And if I got a little ruler, I can measure the length, the width, and the height, and boom, I got the volume, right? Now, so I can do the calculation, the mass of my Hershey bar divided by the volume of the Hershey bar. Now, what happens to the density? What do you think happens to the density if I take this Hershey bar and I break it in half? Is there any change with respect to density of the two pieces, or are they the same? What do you guys think? Okay, they're exactly the same, right? Because when you cut it in half, what happens? That ratio of mass over volume changes. It's the same ratio of, let's say, for example, 1/2 versus 5/10. Isn't that the same ratio? Well, that's what density is. The numbers will be different. So my Hershey bar now has half the mass and also has half the volume. It has the same ratio when it was intact than it does when it's cut in half, okay? Now, however, think about this. If you heard the old line where they say, okay, I got a ton of steel and a ton of feathers, okay? Don't we all agree that they're both the same mass? Of course, I got a ton of each, okay? All right, so what if you're asked, well, which one has a higher density? Okay, a ton of steel or a ton of feathers? What do you think? What do we got here? Okay, we got steel and we got the same. Okay. Now let me add something to this question, because you all done this, especially you got kids. All right, you go to the grocery store, you buy a loaf of bread. Okay. That loaf of bread has a volume. You can measure it, an estimate, length, width, and height. I can weigh it, right? So I have a known density. All right, for that loaf of bread. Now, and this is all going to come back to the steel and the feathers. Now I take that loaf of bread and squish it. You ever have one of the kids after the grocery store? You take that bread and you squish it in. Okay, so squish that bread in. Now, what do you think happens to the density of that loaf of bread? Does it stay the same or does it change? With respect to the loaf of bread, it changes, right? Did the mass change of that loaf of bread when I squished it? No, of course not, right? Unless I took some slices out and I ate some, right? Yeah, but what changed? The volume did, right? And so now with the volume changing, I got a whole new volume. In fact, now the volume gets smaller. And so in that numerator, that volume of that bread that was in its original volume gets smaller. And what do you think happens to the density now? More dense, okay? It has become more dense simply because the volume got smaller. So that numerator got smaller, that number goes up. Now going back to the steel and the feathers, obviously the steel has an X amount of density because it's a solid chunk of material. If it's a billet, a big block, we can measure the volume of that. And obviously we got a ton of them, we can calculate its density. But what about the feathers? It depends, right? Because we know that the feathers are squishable. So the density could be of those feathers. I could squish them enough where they can actually be as dense as that steel. And so the answer for that question is it depends. Depends on the volume of the feathers, okay? And that would vary depending on the volume. So it's a ratio, okay? Density is a ratio, keep that in mind. And that's why ice floats. I explained that earlier in the previous time we talked, where you take a gram of water and at room temperature, it has a X volume. 1 gram of water at 25 degrees has a volume of, I think it's 20 or 25, has a volume of 1 milliliter, okay? I weigh out 1 gram of water, it has a volume of 1 milliliter at that temperature. 1 over 1 is 1. So the density of water at that temperature is 1 gram over 1 milliliter. Now, if I take that same gram of water, water has this crazy property that it actually expands when it freezes, because the way the structure of the waters come into play is very crystalline, very specific, it expands. So that 1 milliliter of water at that temperature now could be maybe 1.1. So now your ratio is 1 divided by 1.1, which is approximately 0.9 grams per milliliter. And so the density of ice, which is still H2O now, because its property as a solid, its density is now less than water, which is 1. And we use the water as kind of a benchmark that says anything less than 1 will float. Anything with a density less than 1 will float. Anything with a density greater than 1 will drop like a rock, okay? All right, so that's why ice floats, and because the density gets bigger excuse me, gets smaller because the volume gets larger with respect to the water. All right. All right, here's some questions here that I'm assuming hopefully you can say, well, this makes sense. Is the state of a matter, which state of the matter is the most dense? Well, obviously it would have to be the solid, right? Because again, we have a known volume with respect to solids. In the least dense would be the gas because their volume, definitely varies quite a bit. There's a lot of space in between, relative space in between gas molecules. And there's some examples of density. You got air and water. Water at standard at 1 gram per cubic centimeter or 1 milliliter, okay? Where gold and a lot of metals are very, very, very heavy, 18, 19, 17, they drop like a rock. And gases, you can see they're very, very low density. Okay. Now, with respect to density calculations, we have 2 types of calculations. One, simply we're going to calculate the density. Okay, and that's real straightforward. We take the mass and divide it by the volume. Now, the volume we can either measure directly with length times width times height, and that gives us the density, or we measure it by displacement. Okay, and it's a straightforward mass over volume. Now, with respect to the second type of calculations, we can calculate from the density either the mass or the volume of that particular material that we're trying to calculate. Because remember, we have the density of units of mass over volume. And we can set that unit either as volume over mass or mass over volume. Okay, just like dollars per hour or hour per dollar, or miles per hour, okay, and hours per mile. And we use that unit by keeping track of our units. We use that conversion factor to calculate what we're looking for. All right, for example, density of chloroform. Chloroform is a chemical that they used to be used. I don't know if they still use it, but I remember as a kid, I had my tonsils taken out and then put a mask on my face and threw some chloroform, and I was out like a light. Anyway, chloroform has a density of 1.48 grams per milliliter. And let me give you some additional information here. A question here. Get your gears working here. Okay. Here we're telling you that chloroform has a density of 1.48. Okay. Now I'm going to also give you some more information. Chloroform is not very soluble in water. It's oil-like. Okay. We'll learn more about that. Okay. So the question I ask you, obviously, if I put a little bit of chloroform and some water together, I'm going to get 2 layers, just like Italian dressing, an oil layer and a water layer. Okay. Now, can you tell me, based on the density, now given that density of water is 1 gram per milliliter, and the density of chloroform is 1.48 grams per milliliter, okay? Can you tell me, if I put this in a container, okay, so I got a liquid, so I want to get 2 layers, okay? Can you tell me which one, okay, well, we got water here with 1 gram per milliliter and chloroform, wrong, right there, 1.48 grams per milliliter. Which layer will be the chloroform in this example here? Would it be the top layer or the bottom layer? What do you guys think? It would be the bottom layer, simply because the density of chloroform is 1.42, and using your benchmark as water as 1 gram per milliliter, anything greater than 1 will sink. So the chloroform will be down here. And this is cool because you can make different layers with different colors, because there are some dyes that dissolve in chloroform but not in water. Okay, and there's some dyes that dissolve in water but not in chloroform. So you can sit there and play with it. Both of them are clear liquids, but with putting in certain dyes, you can have some crazy nice effect here. Anyway, good, you guys got that. All right, so with respect to the density, keep in mind, it's a ratio. So I can write it either as 1.48 grams per 1 milliliter or 1 milliliter per 1.48 grams. Which one I utilize depends on the question being asked and what I am calculating and looking for. Keep in mind, notice here, if I use it on the left, the factor on the left, I am looking for grams, okay? If I use the factor on the right, I am looking for milliliters with respect to units. So that tells you which one, how to set it up properly, okay? Down the road, we're gonna be doing things like I'm gonna give you a general equation, chemical equation. We're gonna be dealing with specific equations, okay? And I may wanna know, all right, if I start off with, let's say 10 grams of A, I may want to know how many grams of C I'm going to make. I'm only concerned between the relationship between A and C. And notice something, that number in front gives me a ratio, see that coefficient, 2C over A. And that is how I set up my problem because I'm looking for C, so C is going to be up here. And I'm gonna take 10 grams of A. Notice my A's cancel, leaving me with C. And that's how I get to the final product, okay? By using this ratio, keeping track of your units. All right, so with that information, then we can figure out, do some calculations. For example, what is the density of my necklace? Sorry, I don't have a necklace. Oh, yes, I do, I guess. You got a crucifix, so I guess I'll qualify. What is the density of the necklace, my necklace, if 484.56 grams, if it had a mass, okay, of 484 grams, 484.56 grams, and they had a volume of 25.64 milliliters, okay? With respect to this question, grams, they're asking you for the density, okay? Density is grams over milliliters, okay? You're given the grams, you're given the volume, you simply plug it into the equation and do the math. Keep track of your sig figs. Note here, 484.5 has 5 sig figs, and 25.64 has 4 sig figs, okay? And so we're doing a division, therefore our answer is dependent on the number of sig figs that I'm using, and so 25.64 has 4 sig figs. Our answer should have no more than 4 sig figs, okay? All right, so we put the number in there and voila, okay? Don't forget that you can, let me do something real quick and check something. 8, 4, 5, 6, 2, 9, 4. Okay. This is the number that you get in the calculator. Okay, and so obviously you wouldn't report that number, okay, because you know you're going to have 4 sig figs. Okay, so that's what your calculator gives you. At least that's what my calculator gives me right there. And given the fact that we should have no more than 4 sig figs, I go to the 4 sig fig position, which will be 1, 2, 3, and 4. That would be the 9. Okay, I look at the neighbor. Neighbor is greater, using the rounding rules. Neighbor is greater than or equal to 5, greater than 5. So the 9 gets bumped up to the 10. So here we got to carry the 1. So the answer is 18.90. Okay. All right. Now, in this scenario, previous scenario, we're doing a real simple calculate the density, mass or volume. You got the mass, you got the volume. There you go. Plug the numbers in, keep track of your sig figs. In this scenario, you're being asked to, given the density of chloroform, okay, how many grams would 17.5 milliliters of chloroform mass? So if you were to take a volumetric flask and measure out 17.5 milliliters of chloroform, the question is, what is the mass? Now, yes, you could take it and weigh it, and that would be fine, but no need to, because you know the density. And from the density, knowing the volume, you can calculate the mass. The same token, knowing the mass, you can calculate the volume, okay? And so we write down, like any problem, we write down what we're given, 17.5 milliliters of chloroform, okay? What are we looking for unit-wise? Question asks, how many grams? So we're looking for units of grams, okay? Which means we're using density here. So I need a factor here that I need milliliters in the denominator. Why? Because I want to cancel those guys. And I want grams to be in the numerator, okay? So 1.48, so I got 1.48 in the numerator and 1 milliliter in the denominator. So that's, I got it set up properly. Okay, your answer here should only have one set of units. For some reason, I see a lot that people come and, you know, the question says how many grams. So you should only have one set of units grams, but for whatever reason, people tend to put density as the answer. And though they got the number correct, the units are incorrect, okay? So no, it's not grams per milliliter. You're not calculating density. You're calculating the mass. So you should only have one unit. Okay, let me clear this up. So we got 25.9 grams of chloroform, okay? Notice our units cancel here, milliliters, leaving us units of grams, which is what we are looking for in the problem, okay? All right, now in this case, they're asking us, well, what if you were to measure out 0.735 grams of chloroform? And you weigh that out. And the question is, well, for whatever reason, you need to know the volume. Okay, well, that's a small amount. That means it's to be tough to measure the volume, but so you calculate it, okay? And we set it up like we just did. What are we're given 0.735 grams of chloroform, okay? What are we looking for? Units, we're looking for units of milliliters, okay? So that means, that tells us how we're going to set up the conversion factor. Density is still the same density, chloroform, but this time we want units, grams in the denominator. Why? Because we want them to cancel out, and we have milliliters on top. So therefore, it's 1.48 in the denominator and 1 on the numerator. Okay. Now it's keep track of your sig figs in both cases. We've got 3 sig figs. Note, density is a measurement and therefore could play a factor in your sig figs. Okay. Again, density is a measurement. It's a measurement of grams, mass over volume. So they're not exact numbers. So it could be a factor with respect to your final sig figs. Got that set up. And check your units. Okay. and check your sig figs, and you're good to go. So again, when you're doing calculations, you're using or using density, any density, the final answer should only have one set of units. That's what you're looking for. Read the question. How many milliliters is the second question. First question, how many grams? Okay, that is what the units will be for the final answer. Right. So any questions about density or the calculation of density? Okay, no questions so far? Because we're going to kind of shift gears a little bit and just talk about something that you're already aware of, and that's about energy / heat, okay? Yeah, for example, that hot molecules move fast, okay, because they have a high energy. Remember that the movement of molecules, two types of movement. There's internal movement in which the molecules within the molecule, the bonds are moving back and forth. And then there's, I want to say, external movement, relative movement to other molecules, okay? And so when you have a solid like ice and you put energy into the system, okay, it excites the molecules and they start to pick up what we call kinetic energy, and they're going to start moving a little bit more relative to each other, okay? And eventually it goes from a solid to a liquid because we have broken in the solid state, that interaction between the molecules is pretty strong. And if we put energy into it, we break up the interaction between the molecules, okay, and make them a little loose, if you will. And if we continue to put more energy into them, we really break up that interaction and spread them out even further. And now they're really moving around, okay? And they have high energy. And if we take that high energy and remove it, reduce it, take the energy away from that system, the molecules get cold and they start to slow down relative to each other. And as these molecules start to slow down, guess what? The interaction between them gets stronger and they start to go from, say, the gas to the liquid state. They start to interacting with each other more strongly and as they slow down, okay? Because their energy is lower. Now, think about this way. Maybe you can look at it this way. We're all familiar with, well, maybe not, but let's assume we're all familiar with taking a hot shower, okay? Some people like tub baths. But let's, you're in that nice hot shower. I like it like burning. That's me. All right. So it's a cold day. It's winter time. And so you turn the water off and you come out of the shower. Doesn't it get cold when you step out of the shower? So what do? And you jump back into the shower, right? To get warmed up again. Well, let's put this in energy perspective. All right, so you got the hot shower going on, it's splashing on you. When you first walk in, you are of lower temperature, of lower energy than that hot water. And rule about the transfer of energy, spontaneously, energy goes from a high state to a low state. It's going downhill, okay? Yes, we can kick it uphill, but you got to put energy into the system to go uphill. But normally, spontaneously, it goes from high to low. So the high heat energy of the hot water is transferred to your body. Your body absorbs it very readily because it's lower energy. Until you're in there, you know, in the beginning, it's like real hot, but then what happens? You get equated, right? It feels okay, all right? So you're steaming. So what do? Now you step out of the shower. You are at a state of a higher energy state than the environment. And so what happens to the energy? It goes from your body to the environment outside the shower. And what happens to you? You get cold, right? You're transferring that energy over. So what do? Your energy drops, your body energy drops, you get a little colder. So you jump back into the shower you just left and close shower currents that warm up again. Why? Because that energy of that shower is still now higher than you. Before you were equated, but now because you stepped out, your energy drops. And now the energy from the shower gets transferred back to you and you warm up again. Okay, so it's a function of transferring energy back and forth, back and forth. All right, and spontaneously, we always go from a high state to the low state, which is important because we're going to learn about electrons, how they get excited to go to a higher state energy level, but then they don't hang out there very long. They drop back down, okay? And when they do that, they release energy of the same amount of what they gained to go up there. And we see it, we can see it as light. All right, so temperature, as we know, is measured with a thermometer. And we have 3 scales, okay? First scale, obviously, is the unit, the English unit is the Fahrenheit. And then the metric unit scale is the Celsius. But there's a third scale, a scale that we use in science a lot. Bathrobe, okay. Yeah, I just saw your warm up there. Yeah, that'll work. All right, oh yeah, okay. So we got 3 scales of temperature. The English unit, which is in Fahrenheit, Celsius, which is in centigrade, or the metric unit, I should say. And then K is a factor unit from English scientist called Kelvin, Lord Kelvin. Now, the thing about both of these, the Fahrenheit and the Celsius, is this. Both of these units go to infinity as far as numbers are concerned. Okay, infinity is supposed to be infinity. Okay, it could be F, a Fahrenheit or Celsius to whatever value, and then the same in the opposite direction. Okay, Kelvin does not. Kelvin stops at 0. Okay, there isn't a negative Kelvin. Okay, this point is called absolute 0 using Lord Kelvin's scale. That is what has been proposed, that matter, all matter, essentially stops moving. We haven't reached 0 yet. We've come pretty close. And what's happening down there, once we get down in these temperatures, there's some whole new physics going on down there, a whole new ball game going on. Totally different and very fascinating. But we haven't reached it. So at that point, absolute 0. But the other numbers, they go to infinity as far as the scales is concerned. Now, when we do calculations, specifically when we do calculations with gases, which would be the last chapter, we have to use the units of Kelvin. Now, there's no relationship between Fahrenheit and Kelvin, okay? There's only a relationship between Celsius and Kelvin. So if you want to convert, you want to know the Kelvin temperature, you have to start off with Celsius. And then once you know the Celsius temperature, you simply take Celsius plus 273 to give you the units in Kelvin. All right, so if you know Fahrenheit, when we'll give you the equation here in a second, to get from Fahrenheit to Kelvin, I gotta go to Celsius first, and then from Celsius, I go to Kelvin, okay? All right, and that relationship is given to you in the shapes table. Here's Kelvin, and it's as follows. So to calculate the temperature in Celsius, if you know Fahrenheit, you simply subtract 32 from Fahrenheit, and then you divide that number by 1.8, and that gives you the temperature in Celsius, okay? Now, if you wanted to do just a rough estimate, but not for calculations, you just wanted to know, You take your Fahrenheit, subtract 32, divide by 2. Ballpark, big rough estimate. Don't do that for actual calculations if you just want to know what the temperature would be about if you knew the Fahrenheit and you want to go to Celsius. And the same is true if you start with Celsius, you go to Fahrenheit. If you want a rough estimate, multiply by 2, then add 32. But to an actual calculation or an actual problem, multiply by 1.8 Celsius times Celsius, and then add 32, and that gives you Fahrenheit. Okay. Now, once you know Celsius, you just simply add 273, and that gets you to Kelvin. With that information, and like I said, you don't have to memorize that. Why? Because it's on the shapes table. It's one of the tables you use, and it's there. So no need to memorize it. It's right there. And so when you get a chance, try 150 degrees Fahrenheit, convert that to Celsius and Kelvin, and you should end up with 46 Celsius and 319 Kelvin. Okay. So try that calculation in your own time and see if you come up with those numbers. If you do not, let me know. Next Tuesday, obviously, is your exam for chapters 1 to 3. I'll be here. We'll do a lecture, but I also will use that time if you need to answer any questions for these chapters that you want. Yeah. And what are we, for us at 1:30, a simple 273 is sufficient. Yeah. Okay. Yeah, simple 273 is fine. If we were doing, if you go up to 151, 152 chemistry, we're going to have to get more specific. All right. All right. So with respect to energy and heat, you know, we're looking at 2 containers here. Okay. Now, the question is, which of the 2 beakers has a higher temperature? You know, and the first time I looked at this, I'm like, what? You know, that's a pretty silly question, but you know, you look at it and you say, okay, hey, wait a minute. That red stick must represent a thermometer, obviously, right? A and B, it looks like some liquid. And obviously A has a lot more volume than B does, okay? And obviously it's been heated, and guess what? They both have the same temperature, 100 degrees, okay? All right. But which has the greater amount of heat / energy, okay? And that would be A, right? Simply because there's more material in A. You know, put it to you in this perspective. This is a bad analogy, but it really puts it in perspective. I got a big pot of water that I'm going to use to boil. I'm boiling some water to make some spaghetti. It's a big old pot. Then I got a little tiny little half-quart pot of water, making a little, maybe a cup of tea, warm up a little bit of water. They're both boiling, right? They both are boiling at the same temperature, okay? But if I had a choice, and I was given a choice, which one do you want to spill on you? What would you select? The little tiny pot or the big pot you're using for spaghetti? Well, obviously, the little tiny pot, because there's less. They're both boiling at the same temperature, but there's less mass for that little pot, and there's less energy in that little pot. So yes, it's going to burn, but not as bad as that big giant pot. Okay, there's more molecules, and that's why it takes. Think about this. That's why it takes a lot of time for a big giant pot of water to boil, relative to say a small quart of water to boil, because there's less material in the small quart. It's going to heat up all that water molecules quicker because there's not that many of them, and get it to boil much quicker than a big giant pot you're saving. You want to put some spaghetti in, right? Okay. And the water has a unique property, and it can retain heat. Are you familiar with the term, with respect to weather? You may hear the term El Nino or La Niña. Does that mean anything other than little kid, little boy, little girl? Does that mean anything to you with respect to temperature? And so what is a tornado? Not quite. It can have an effect to result in tornadoes and all kinds of things. But what it is a body of water out in the Pacific. And the only difference between El Nino and La Nina is the quantity of water, the quantity, the size of the body of water. And this body of water has a temperature differential different from the rest of the ocean. Not a lot, 2 to 3 degrees difference, but there's so much quantity of water that it has a big effect on the world temperature, okay? A big effect on the world temperature. The oceans are not all uniform with respect to temperature. I don't know if you've ever been in the river, you've been in the ocean, you've been in a swimming pool, and there's like gradients of temperatures all around you. It's not uniform. Anyway, that's one of the properties about water. It has a lot of specific, very high specific heat, holds a lot of energy. All right, enough of the side note. Heat transfer. As I mentioned before, nature being nature goes from high temperature to low temperature, okay, spontaneously. Yes, it can go from low to high. We do that all the time. When you have, if you have your refrigerator. Your refrigerator puts energy into that system for your freezer to work, to get that temperature down. It doesn't freeze spontaneously. You got to put energy into the system to get that temperature down. If you have electrical burners in your stove, it's seasonal, Josh. The El Nino and La Nina. Yes, it's not always out there, just a seasonal. And it has an effect on the weather all around the world. And it's just a big body of water. All right, good questions. Yeah, so I was saying, if you put energy into the system, you have an electrical stove, the burners, you put in energy into the system to get those things hot, right? So you're putting energy, but once they're hot and you turn the energy off, they cool back down on their own. They don't stay up there hot. They drop in temperature, going from hot to low. That's nature being Mother Nature. It's not going to hang out there in the high energy state. It's going to drop back down to what we call the ground state, whatever state that may be. All right, so heat transfers from a high temperature to a lower temperature. So it goes from hot to cold. So, you're making some cookies and you take them straight out of the oven and, you grab a cookie, you're going to go, ouch, right? Because it's hot. Why? Because the cookie coming out of the oven has high temperature. Your hand is low temperature. And so that heat's going to transfer from the cookie to your hand. And it's going to get hot and you're going to burn you. Okay? So the cookie will lose the heat and your hand is, unfortunately, will gain the heat. Okay? Another example, let's take a piece of metal and we stick it in the freezer. Okay? So the metal is then put in a bucket of hot water. Okay? Now, does the temperature of the metal increase, decrease, or stay the same? What do you guys think? Okay? So I got a bucket of hot water. I got a spoon metal in the freezer. Put it in hot water, what happens? It will increase, and that is correct. Okay? Because again, we got a transfer of energy from the hot to the cold. Okay? And, excuse me, does the temperature of the water in the bucket increase, decrease, or remain the same? Okay? So the water decreases because it's losing energy. Okay? Okay, yeah, that's correct, guys. And so, if you got a cup of coffee or a cup of tea and it's a little bit too hot, and you want to cool it down, yeah, you can put an ice cube in there and that's fine, but then dilute your stuff. Or you can stick in a cold spoon and let it sit for a while. That energy will transfer from the tea, the liquid, the coffee to your spoon. Okay, and cool it down for you. Eventually, everything, if I take that hot cup of coffee and I leave it on your desktop, that cup of coffee will eventually go to room temperature. And it's going to displace, get rid of all that heat it had. Okay. All right. So, we got the chapters, work on the worksheets, don't forget the YouTube videos, not only the ones we do here, but Dr. Kim's videos. Okay. Practice conversions, be aware of sig figs, be familiar with that. And of course, you got homework coming up. Chapter 3 should be due this weekend. And if you have any questions about these 3 chapters, let me restate that on Tuesday, even though it's exam day, we'll be here for lecture, but I will always, and for this point forward, because if you look at the schedule, you can essentially have an exam a week. Okay, so you got a lot of stuff going on. You got homework, you got labs, and then plus the exams. So things are going to get pretty tight. Given the time span that we have, and please do your best to keep on top of it. Don't get behind. All right. All right, so any questions, comments, concerns? All right. So we finished that pretty quick. That what we do, let's take a 15-minute, okay? And maybe you can think about what we just finished or any other questions from the other chapters. And when we come back, we can go over these questions. And if there isn't any, we'll jump right into the next chapter, which now we're going to get back into the start of chemistry and talking about chemicals eventually, but get into, we start off with baby steps and we talk about the atom and what's made up of what makes up the atom, and then from there we're going to build on it. Okay, build on it. All right, so let's come back at say 2:15, and then if there are not any questions on chapters 1 to 3, we'll continue. All right. Okay. We'll be right back. Okay. Any questions about the chapters? But if you don't, no problem. We'll maybe this weekend, give you time this weekend to think about them. And on Tuesday, bring them into class and we can go over them, or send me an email. I'll get to it right away, given that you got a test coming up. See what else. All right, well, no questions. I will continue with chapter 4. Here, we're going to start talking about the atoms. Okay. 1 second, I do some adjustment here. All right, chapter 4, talking about the atoms. Now, back in the 1800s, we're going to find here as we go through this chapter that a lot of this model that we have, modern day model, really began in 1800s and really amplified in the 1900s. And you'll see that 1900s, there was a lot of models that came out, a lot of theories that came out about the atom and how things are put together. And just a whole slew of scientists, well-known scientists, famous scientists. This was the era of Einstein era, but he was not alone with respect to this. Anyway, back in 1800s, Dalton proposed an atomic theory, proposed that the element is made up of real tiny, indestructible atoms particles called atoms, okay? Now, it turns out they're not indestructible. It turns out that the atoms themselves are made up of even smaller particles, subatomic particles, which, we're going to talk about those with respect to the three main ones. And then years later, we find out that these particles are made up of even smaller particles. But we're going to stop it at the proton, neutron, and electron level, okay? Okay, another part of this theory is that all atoms of an element are identical and have the same properties, okay? Again, this, we find out it's not quite true. Case in point, the diamond we just talked about. Diamond made up of carbon, okay? Carbon with six protons. Same carbon that is utilized to make up, the carbon in your body, okay? But, depending on how they're put together, totally different properties. So, also along the lines here was Dalton's additional theory that atoms of different elements combine to form compounds, okay? And that still remains true. That's how we define a compound. It is a atom, two or more. It is a material that is combined by two or more different atoms. You can see here two diatomic elements coming together to form two different, two compounds, okay? In other words, a red combined with the green to form a compound. Additional part of this theory is that when atoms come together, they come together in small whole number ratios. For example, the formula for water, as we know, is H2O. Okay. We're in here. Where do you go? H2O. We write a 2 here to show you that there are two hydrogen atoms. Note that number 2 is a whole number. The subscripts that we utilize are always in a whole number, okay? They don't come together as half atoms or 3/4 atoms. They come together as whole units. Now we write this is a shorthand way of writing the formula for H2O, because what's happening here, we're going to learn that we have oxygen bonded to two hydrogens. It kind of gives the impression when we write it H2O that the two hydrogens are bonded to each other. That's not the case at all, okay? Not like H2, which is hydrogen gas, totally different, okay? The fact that if you ever see H2 and then there's another element following immediately right after this, that should indicate that those two hydrogens are not together like hydrogen gas, but are actually bonded to the atom next, whatever is shown next. Another example would be H2S, okay? That's another example of a compound, and very similar means of water being bonded together. Anyway, they come together in whole numbers as far as the atoms are concerned, okay? Another part of his theory is that when atoms of two or more elements come together, they can come together in different ratios. For example, CO, carbon and oxygen, can come together to form either carbon monoxide, okay, carbon monoxide versus carbon dioxide. Notice the names here. Carbon monoxide, which tells you that there's one oxygen, mono, versus carbon dioxide, which tells you there are two oxygens, okay? A quick note about nomenclature. That, what I just talked about, is called nomenclature. That is naming the compounds. When it comes to, earlier I stated that when a non-metal and the metal come together, they form what's called an ionic compound. And when two nonmetals come together, they form what we call a covalent compound. when it comes to naming these compounds, covalent compounds, that is what is made up of nothing but nonmetals, we use prefixes, like carbon dioxide, carbon monoxide. When it comes to ionic compounds, which is metal and nonmetal, no prefixes. But more on that down the road here, okay? Just giving you a heads up on that. Okay. So they can come together in different ratios. Now, 1897, we're getting closer to the turn of the 19th century. We start early 1800s, we've got Dalton, and then we got British scientist by the name of Thomson, okay? Good old JJ. Now, he is credited with discovering the electron, okay? Now, up to this point, remember, it was not, here we got an atom and that's it, all right? Okay. Now we're starting to learn about what that atom is made up of, and these are the subatomic particles that we're going to talk about. And JJ was the one who's credited with discovering the electron. Okay, so we're going to listen to a little video.
We can't hear it.
Okay. So in this experiment, a quick question, somebody had a question about bi, that. No, for prefixes, we don't use the prefix bi. We're going to use mono, di, tri, and we'll get through those prefixes, but bi is not one of them, okay? All right, so in this scenario, J.J. Thomson is generating some particles. Now, what you're looking at is the precursor of what we now, we call the television, okay? The old-fashioned big rear-ended television heavy, because what's happening here is this, a particle is being generated denoted by red. Now, on the forefront here, up here, there is the screen, which has a material coated on the screen, phosphorescence material. Now, what's happening is these red particles, okay, are highly energetic, hit the screen, they transfer that energy they have onto the material on the screen. And that material, earlier I was telling you about when we talk about energy, Mother Nature is such that it doesn't like to hang out there in a high energy level. When it gets excited to an excited state, it will drop back down, okay? And so that energy from the red particles is transferred to the material on the surface here of the screen. They excite the molecules, it excites the molecules on the screen. They go up through the excited state, but then they're going to drop back down. And what the amount of energy they gain is lost. It has to be an equal amount of energy, and it loses it as light. So we're sitting over here, you're sitting over here looking at it this way. Here's an eye looking up here, okay? Looking at the screen, and it gets excited, okay? This is how the old-fashioned television screens used to work, because back in the back here, we had 4 big old magnets, okay? And then it shot a screen up here. It took the television signal and converted it to, gave you information, and then eventually you create a beam, and it scanned on the screen here, and it created an image, So a lot more complicated than I just demonstrated, but this is the precursor of the television screen. So here's JJ. He's finding that he's creating this particle, and he sees it, okay? Exactly. Josh, does it know CRT, otherwise known? Anybody know what a CRT tube is? What the name is? Cathode ray tube. Okay. So precursor for your television. Let me clear this up. And Notice here what's happening. They put a plate, positive and negative plate, okay? And they run that tube and deflects the tube. Notice that? Deflects the tube. And what that tells you is this. If that particle is being deflected, then that particle must be charged, okay? There's got to be a charge in the particle. Otherwise, the plate here would have no effect, okay? And notice in this example, the tube gets attracted to the positive side. So what can one deduce from that? That this particle, whatever it is, and it eventually becomes an electron, has a negative charge. The negative gets attracted to the positive, okay? If it was positive, it will be deflected in the other direction, but it's not. Okay. All right. The video has no sound. Is everybody not hearing the video? No sound. That. No sound. No sound. Okay, give me a second. Let me find out what's going on here. Good.
Is attracted by the plate bearing.
How about that? Did you hear sound there? All right. Okay. Well, let me back it up here because you got to hear the sound here. Let me start it again here.
Cathode ray tube is the
If you don't hear sound, let me know.
forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube.
Okay, this is where we ended up here before. I didn't realize you had no sound here. But we put an applied electrical field and it causes a deflection of that particle. Okay, notice how it deflected down. And it's deflecting toward the positive side, which then you can deduce that if it's being deflected, this strongly suggests that this particle must be a negative charge particle, okay?
The cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it.
Okay. Now, any charged particle has along with it a magnetic component, okay? Which is a good thing because that's how we can make electric motors and generators, okay? Because we're playing either with the magnetic component or we're playing either with the electron component. So notice here that a magnet is placed in on the cathode tube and it deflects that ray. And that's where the old-fashioned televisions came into play. If you ever take one of those apart, back in the back, that's why they were so heavy. There was 4 big, giant, heavy magnets, you know. And anyway, so it has a magnetic component, this charged particle, okay? And then a applied magnetic force deflects the particle.
Can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection.
Now, obviously, this equation is beyond the scope of Chem 130, but the point to take away from this is that JJ was able to determine this ratio right here. That is the charge to a mass ratio, which then gives one the opportunity, if we know what E is, because we obviously have this information, if we know what E is, guess what? We can calculate the mass. Okay, obviously we can't weigh it directly, so this is an indirect calculation what the mass would be. Okay, so that's the takeaway from this equation.
Deflection. B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay. So from
A cathode ray.
So from his experimentation, okay, he determined, again, that at 1904, proposed a model for how the atom is, what the atom is made up of. So he proposed that the atom, they have a model called the plum pudding model, whereas somewhere in the atom was a positive charge area, and that these negative charge particles were somewhere on the outside of the atom, okay? Very general model, okay, because not enough information is known, okay? So with that came another scientist, good old Rutherford. Note the time. 1904, we're at 1900 there. And then here we go, 1911. This is also the time of Einstein and his work. And there are a number of other scientists that are working on different models for the atom. So Rutherford comes along. Now, he is credited with discovering that the atom is made up of a heavy, dense nucleus. So we have JJ's theory about the electron, that the electron's somewhere around on the atom. And then, but there's a positive component, we don't know for sure what it is. And here comes Rutherford. And he proposed from his work that there is a nucleus. And in the nucleus, there is a particle, a positive particle, okay? Now, he also generated some particles, specifically alpha particles, and he bombarded them into a gold foil, okay? And let's look at his video, and if you don't get any sound, let me know, please.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected.
Okay, so very similar to JJ's work, where he's getting his particles being generated, okay? And then he has this fluorescent material around. So these particles come across, okay, in the excited state, they hit the material on the fluorescent material and they excite these particles. So they actually, you see something here, okay? So here's the kicker about this. If the plum pudding model was accurate, I should say, was a good model, if you will, then what should be happening here is that that's all he should see. This is particle. But he starts seeing deflections. things were bouncing off at different angles. Some of them even went all the way back to the source. And so, things were being deflected, much like shooting pool. You hit the cue ball, you hit a ball, and it's going off at an angle, right? So something else must be going on with respect to the atom. So let's continue.
However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay. And so in Thomson's model on the left, the plum pudding model, then all these particles run by Rutherford would go through, okay? But what Rutherford was findings was some deflection. And so that suggested because the relative size of the particles are so small that it must encounter something that's pretty dense. And so what he was proposing that there is encountering the nucleus, okay? And in the nucleus is what we have, what is the positive, the proton area. So we have the model where we have a nucleus where the proton exists, and then the electrons are somewhere orbiting around the nucleus. We'll get more, not an accurate, but we'll get a more refined model on this here in a bit. Okay, so in 1917, Rutherford actually discovered nucleus/proton, okay? It wasn't until the 1930s, another scientist by the name of Chadwick, he discovered what is now known as the neutron, okay? And so we have JJ noted for discovering the electron. Then we got Rutherford noted for discovering the nucleus/proton. And then with Chadwick comes along and he puts his 2 cents and he's noted for discovering the neutron. So that model on that picture on the right kind of depicts what the model is of the atom, where we have the nucleus, which has the proton and the neutron, okay? And then orbiting someplace outside is the electron, okay? And in the middle there, we have the proton and the neutron, okay? We find out that the proton has a positive charge and the electrons have a negative charge, and the neutron, hence its name, is neutral in charge. Right. Well, we also determined, what has also been determined, that basically the atom is a lot of empty space. And to give you, well, I got some examples here, but to give you another perspective, if, let's say, for example, I was scaled the size of the atom to me, and so I got the atom with my nucleus, and I got hydrogen has 1 electron, okay? That electron will be roughly approximately about 3/4 of a mile away from me, okay? A lot of empty space in between, a lot of empty space. And a lot of energy interacting between the proton and the electron. The atom has a ton of energy. Hence, in point, the atomic bomb, the hydrogen bomb, a lot of energy involved there. Okay. So each atom has a small dense nucleus with the protons and the neutrons. Another example, if the nucleus was the size of, let's say, a small marble, then the atom radius, okay, diameter would be the size of Cardinal Stadium, okay? A lot of empty space. So we have a table here that tells us information about the electron, the proton, and the neutron. All right, so we have a symbol for electron, which is lowercase e, and it has superscript hyphen, which represents the negative charge. Okay, proton has lowercase p with a superscript positive because of positive charge, and then lowercase n for the nucleus. Its location, this the electron is outside the nucleus, whereas in the nucleus is made up of the proton and the neutron make up the neutron. Okay, there's their respective charges, and then the relative mass. Because the masses here are so tiny, what's been done is they gave them a relative mass. Okay, for example, the proton and neutron have a relative mass of 1. But think about this one. All right, let's say, for argument's sake, I'm at 200 pounds. Somebody else is at 400 pounds. So the relative mass, I could be set at 1, and since someone else is, twice my weight, their relative mass is 2. So they got a relative mass of 2, okay? And that's what we call the AMU, atomic mass units. These are relative masses. They're not absolute masses. So proton and neutron each have a relative mass of 1. The electron is so tiny that for all intents and purposes, it is given a relative mass of 0 because being so small. Bear in mind, it has mass, but because it's so small, it's considered to have no mass. All right. Okay, so there's some relative masses. Almost 1/2000 of a relative mass. Atomic notation. Now, if we look at the periodic table, we have, got a question here. Give me a second. Yes, we'll learn about the electrons, and we're going to learn, Eduardo has a question, does the electron create like a cloud around a nucleus? And the answer is yes. What's happening here, what we're going to learn is that the electron is orbiting around the nucleus, but is orbiting around specific energy levels, okay? Specific energy levels. And they orbit around specific types of orbits, okay, that are mathematical equations. And so what happens is this, that any mathematical equation, we can take it and plot data to it. They happen to be three-dimensional, very complicated mathematical equations. And the result is, if you plot a lot of data, they give you this area of the probability of an electron being in a certain area. But from a picture perspective, it looks like a cloud. And the question is, well, can it exist in this area? Yeah. There's a probability that, yes, it could exist in this area, but it can also exist in a different area. And what the result is, we have these images of these orbits of specific shapes that come from mathematical equations. More on that when we get to the specific energy levels, okay? All right, that's a good question. Oh, one more. Yes, electron shells. The shells are really the energy levels, but within the shell, we will find subshells, what we call orbits. Okay. All right. Well, with respect to the atoms themselves, we have what's called a atomic notation. Okay, where SY represents the symbol of the element. Okay, superscript left is what is called the mass number, okay? And subscript left, Z here, is called the atomic number, okay? Now here's the thing about the mass number. Since the mass number, this is a whole number, always a whole number. Not to be confused with the atomic weight, which is a decimal number. That is that number below the symbol if you look at the periodic table, okay? The mass number is a result of the total number of Well, I will do a specific example. I don't want to give you confusing information. We'll get that here in a second. Okay, so let's continue. The atomic number is you get from the periodic table, okay? Because if you look at the periodic table, the number above that symbol is the atomic number. Okay. What the atomic number represents is two things, okay? For the elements is the total number of protons and the total number of electrons. All right, so if you look at the periodic table, at a glance, you can select any element and based on its atomic number, which is right here, let's take a look at carbon. Carbon's right here, number 6, okay? Its atomic number is on top of the symbol. Carbon, elemental carbon, has 6 protons, 6 electrons, okay? Nitrogen, its neighbor, has 7 protons and 7 electrons, a total. Oxygen has 8 protons, 8 electrons. Gold has 79 protons and 79 electrons. And so if we continue with, any element, if we look at barium, right here, Ba, number 56, 56 protons, 56 electrons. Now here's the thing about the three subatomic particles: protons, electrons, and neutrons. Protons and electrons. We can lose or gain electrons and neutrons all day long, and we'll never change what that element is. What defines an element is the number of protons, okay? I'm gonna repeat that. What defines an element is the number of protons. The moment I change the number of protons, I have a new element. For example, let me clear this up. If we look at lead, and then we look at gold, okay? Gold is 79, it has 79 protons, where lead is 82, it has 82 protons, okay? They have different number of electrons, that's okay. But if I were to gain a proton for gold, it become number 80, which is mercury. Totally changed the new element. Now think about this. For alchemists, I don't know if you know, alchemists are the precursors of the modern day chemists, but is that Harry Potter stuff. You know, they tried always to take lead and convert that to gold. Well, in order for that to happen, I got to lose some protons. And where are the protons? They're in the nucleus. And if you split that nucleus, you got a big problem. Okay, splitting of an atom, you end up with a big boom. So it's not as easy as it looks. If you can find a way to do that without not blowing up the earth, hey, that'd be great to make gold. But then if you find how to make gold, then gold will be worthless because you can make it and it won't be worth as much. All right, so let's go back here. So atomic number tells you how many protons and how many electrons. Now, when we lose electrons, and remember I told you way back when to put this in long-term memory, all metals want to lose electrons. All non-metals want to gain electrons. So you're going to learn here in a bit why that's the case. But the ultimate goal when we're losing electrons or gaining electrons is these elements are trying to get to the magical 8 electrons around its outermost shell, okay? more detail on that to come. And so when we lose electrons, we form these ions. So when you're ingesting sodium, potassium, whatever, you're not ingesting the element, you are ingesting the ion, which is the element that has lost electrons, okay? All right, there's more on this. Now, the mass number is a whole number, as I stated. And that is the sum number of the protons and the neutrons. Remember the AMU, the atomic mass unit, the relative mass unit, made up of 1. So you're going to have X number of protons, a whole number, X number of neutrons, a whole number, to give you the mass number. Okay. All right. So if you know the mass number, if you know the protons, guess what? You can calculate the neutrons. Right? It's an algebraic equation here. Now, every atom of an element has the same number of protons, because that is what defines an element. Okay? And with respect to the elements, which are neutral species, keep this in mind. I just showed you in your periodic table, carbon has 6 protons, which are 6 positives, and it has 6 electrons, which are 6 negatives. 6 positives, 6 negatives. What is our net? 0, right? They cancel each other out. Our net charge is 0. So all the elements have a net charge. All the elements, all the atoms, all the elements have a net charge of 0. We're going to learn that the ions are elements that have a net charge of either positive or negative. And that is because they either lost electrons or they gain electrons. For example, if I have 6 electrons and 6 protons, and for argument's sake, let's say I lost 1 electron. Now I got 5 negatives and 6 positives. Do I not have a net positive 1, right? On the same token, if I start 6 and 6, now I got 7 negatives and 6 positives. Do I not have mathematically a net 1? Yeah, okay. And those are the ions that are being created. And depending on where they're at in the periodic table, they can either lose 1 or 2 or even 3 electrons, or they can gain 3, 2, or 1 electrons, depending on where they're at. All right, so as I stated, the number of protons defines an element. Okay, so carbon always has 6 protons, regardless of whether it is carbon in the diamond, carbon in your body, carbon dioxide. It is still 6 protons. The moment I lose a proton, I'm no longer carbon, I'm something else. Okay. All right, so the atomic mass unit. Masses of the atoms are small. They recall that we have to give them, excuse me, relative masses. The proton and the neutrons have an approximate 1 for the atomic mass unit. And the electrons are basically 0 with respect to mass, okay? Now, how do we calculate the mass number? We know by definition that the mass number, again, a whole number, and I repeat that because I want to show you this. On the periodic table, that number underneath the symbol, where'd it go? Right here, carbon, for example, 12.01. That is the atomic weight, not the mass number. That is the atomic weight for carbon. It's a decimal number. It's not a whole number, okay? Now, here's something that sometimes can be a little bit challenging to think through, but we're going to work it through to make sure you understand. Question is, how do we calculate the number of neutrons? Okay, all right. We know that the mass number is equal to the protons plus the neutrons. So we can rearrange that equation and say the neutrons is equal to the mass number minus the number of protons or the electrons if we're talking about neutral elements, right? So what do? We go to the periodic table and we look at the atomic weight, okay? And we round it up to the nearest whole number. And that could be a problem to grasp here. Let me, bear with me for a second. Let's take the example of carbon. I'm going to designate carbon 11, carbon 12, carbon 13, and carbon 14. Okay? We're going to learn about this. This is called isotopes. You've probably heard about carbon dating, okay, carbon 14, okay. Well, what that is carbon. The only difference between carbon 11, carbon 12, carbon 13, carbon 14 is the number of neutrons. Everybody here has 6 protons. Everybody, it's still carbon, okay? The difference is carbon 11 has 5 neutrons. Carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. And that is the only difference between these 4 different carbons, okay, is the number of neutrons. And so they make up what we call isotopes. Now here's the other aspect. If I were to average out the numbers 11, 12, 13, and 14, can anybody tell me what the average of those 4 numbers are? 11, 12, 13, and 14? What would you think those average would be? 12.5, and that is correct, Trevor. Okay, that will be the average of 12.5. Okay, all right, but here's an added twist to it. With respect to concentration, these are all isotopes here that are out in nature. Some isotopes are in higher concentration than other isotopes. Carbon, I want to say carbon 12 is, I think it's about 98% in nature is carbon 12. The rest is 1%, go 13 roughly, and then split amongst the other 12 and 14. Here's the deal. When I average these numbers out now, and I account for the fact that they have a different percentage, just like your grade, there's a percentage for this assignment, percentage for that assignment, etc. The result is, instead of straightforward 12.5, the average for these 4 isotopes and taking into account their percentage in nature, guess what? Turns out to be 12.01. And that is the atomic weight that you see listed underneath the symbol of the element, okay? And what we can do is this. We can take that 12.01 and we can just round it up to the nearest whole number, okay? And 12.01 is rounded up to 12. So the mass number for carbon, in this case, we're talking about carbon, by rounding up the atomic weight, we get a mass number of 12 minus the number of protons carbon has is 6, that's always constant, means that the number of neutrons is equal to 6. See how that works? Now, this is one reason also to keep in mind why we don't use the atomic weights to determine sig figs. And what I said, use the atomic weights we give in the periodic table. Because depending on the source, these atomic weights that you see on the periodic table can vary. You have, that 12.5, which does not account the percentage of each one, the 12.5 average for these 4 numbers, this is the average of whole numbers, 12.5. And so what that means is when you average whole numbers, you end up with an infinite number of sig figs. You're going to have 10,000 of them, okay? And that's why we say we don't use atomic weights to determine how many sig figs you have, okay? But we use the atomic weights to make sure your calculations are correct with respect to chemists, because our answers are based, if you use the atomic weights, on the atomic weights we give you from our periodic table. All right, so that's how we can determine the number of neutrons, okay, from the atomic weights for the elements, okay? And keep it in mind that when we round up that atomic weight, we are rounding up the atomic weight for most abundant isotope for that particular element. Every element has isotopes. Carbon, is an example, has 4 isotopes. Some have 2, some have 3, they all vary, okay? But that number that you see, it's a decimal number, is the result of the average, the weighted average of all the isotopes for that particular element. And you'll find that the bigger size elements have their atomic weights in parentheses. And that's because they're radioactive and they decompose very quickly. So they really can't get a good number on it. So that's why I put it in parentheses. Okay. All right. So clear as mud. All right. So let's, now what happens is this. You will find that sometimes you'll see, I wrote down earlier, I wrote down carbon C11, C-12 earlier. You might find a notation like this. So if you got the simple carbon, we'll say C-11, C-12, C-13, C-14. That's one way to write all the different isotopes, or I can write them out longhand, carbon 11 hyphen, or carbon 12, etc. Okay, so that's what they're doing here. They're telling you potassium 40. So guess what? They are already giving you the mass number for that isotope. You might ask yourself the question, is potassium 40 the most abundant isotope there is? Well, to answer that, you go to the periodic table and look up potassium, which is right here, and look what potassium, its atomic weight is 39.1. And so if I round that up, I get potassium 39. So potassium 39 is the most abundant isotope, okay, based on the atomic weight that I rounded up. So the question says about potassium 40, so that's not the most abundant isotope, okay? And the difference between potassium 39 and potassium 40 is what? 1 neutron. Potassium 40 has 1 more neutron. All right, let's go back. No problem. And so they want you here to write the atomic notation for potassium 40. Well, we got to get the symbol, okay, and that's K for potassium. They give you the mass number there, 40, so I can put 40 up here, okay? And then knowing the atomic weight, I looked that up in the periodic table, that's 19. Okay? So that is the atomic notation for potassium 40. If they were asking for potassium 39, then no big deal. I would have written it as follows. Notice the 2 potassiums. They both have 19, right? They're both potassium. The only difference between the 2 is simply the number of neutrons. So the next question is, well, how many neutrons are there for potassium 40? So it's simply the 14 minus the 19, which is 21, okay? Well, what about potassium 39? How many neutrons does potassium 39 have? Can anybody tell me? Exactly, 20, just 1 less. So it's 39 minus 19, which is 20. So there's 20 neutrons for potassium 39 and 21 neutrons for potassium 40. Both of them are potassium, okay? They differ only in the number of neutrons, or isotopes. Okay, here's another one. They're asking you to write the atomic notation for bromine, 81. Okay, and so we find the symbol for bromine. They give you what the mass number is, because it's bromine hyphen 81. That is the atomic number. And 35 is simply the mass number. The atomic number, the 35 comes from, look it up in the periodic table, it's 35, okay? And the neutrons here are 46, okay? Now, can anybody tell me if bromine 81, is bromine 81 the most common isotope? What do you guys think? And that's no. It'll be bromine 79. Okay, that's correct, Eduardo, because you just go to the periodic table. Okay. Go to the periodic table, look for bromine. Bromine's right here. And round that number up, the atomic weight of 79 point, did I say 79? 79.8, what does that number round up? 79.9 is what? 80, there you go. So bromine 80 would be the most common isotope. Okay, no worries. All right. Now, I talked about isotopes, and here they're talking about carbon 12, 13, and 14, okay? And basically isotopes of an element. Now, hydrogen has three. There's hydrogen 1, hydrogen 2, and hydrogen 3, okay? And it's really, really interesting that if you were to make ice from using hydrogen 2, normal ice, hydrogen 1, you make H2O using hydrogen 1, that ice floats, right? Because it tends to expand when you freeze it. But if you take hydrogen 2, deuterium, you make ice, it actually sinks, it becomes more dense, so it doesn't expand as much as hydrogen 1. So a lot of different properties with the different isotopes. And a lot of these isotopes too are very important, depending on the material they use them for, tracers for in the medicinal purposes, you know, so you can you might drink something or might get something injected, and then you do a CT scan, or you're able to trace where it goes. So there's a big field for making these materials. Okay, so we have carbon 12, 13, and 14. Everybody has 6 protons. Everybody, like I stated, because it's carbon. Where they differ is the number of neutrons. Okay, so we don't have carbon 11 here, but it will be 5, 6, 7, and 8 with respect to the number of neutrons. Okay, so you have a table here, and you say oxygen 16, 17, and 18. Okay, well, they're asking to fill in the mass number. Well, guess what? When they do that, that is that number. So it's simply 16, 17, and 18. Okay, protons. Oxygen is number 8. Everybody has 8 protons. And guess what? Everybody has the same number of electrons. Okay, and where they differ is the number of neutrons. So the sum of these two would equal to the 16, right? So don't make these tables more difficult than they really are. They're, a lot of that information is given to you already, like the mass number. It's right there. This and this you look up on the periodic table. The neutrons then you calculate because that's the difference. Subtract here, here, and here, and that gives you the number of neutrons. Right? And so your table should look as follows. Okay. So carbon 16 has 8 neutrons, carbon 17 has 9 neutrons, and carbon 18 has 10 neutrons. Okay. And this here is a explanation, as I just stated, why the atomic mass is, how they figure out the atomic mass. It's a weighted average, okay? So for example, carbon 11, carbon 12, carbon 13, carbon 14. I was a little bit off. Carbon 12 is about 98.89% out in the nature, and carbon 13 about 1.1% out in nature. And there's minor amounts of carbon 11 and carbon 14, okay? And so by taking their actual percentage of each one, you, instead of having an average of 12.5, like we did, we do a weighted average, and you end up with a 12.01 atomic weight, which is the weighted average atomic weight of all the isotopes of carbon, okay? And that is why you can take the atomic weight and round it up to the nearest whole number, and that will give you the most common isotope for that particular element, okay? Because that most common isotope will be of higher percentage, so the average, the weighted average, will be closer to 12. If carbon 13 was 98%, then the weighted average would probably be, closer to 12.01, 13.01. See how that works? All right. Carbon 13, so that's that. So what we can do is, using the periodic table, okay, we can determine who is the most abundant isotope. For example, if we look at lithium and lithium-6 and lithium-7. And the question is, which is the most abundant isotope? There's nothing here you have to memorize, okay? You just got to find it on the periodic table. We find it on the periodic table, and lo and behold, here we go. Right there, lithium, Li, okay? Its atomic weight is 6.94. Round it up to the nearest whole number, that tells me that lithium-7 is the most common isotope. So I can circle that as the most common isotope. Okay, see how that works? Second question, which is the most common, chlorine-35 or chlorine-37? Well, we go back to the periodic table. Believe me, we're going to use this periodic table immensely. Okay. Find chlorine, which is number 17, okay? Its atomic weight, can't highlight it here, is 35.45. Round that up to the nearest whole number, okay? That's 35. So the most common isotope for chlorine is chlorine-35. Okay. And where they differ is simply the number of neutrons. Okay, the elements, like I said earlier, most of the elements are radioactive and very unstable. And it's always, they're breaking apart, so we really can't get, an atomic weight. So we put them in parentheses, like for example, curium, which is named after Madame Curie, okay? And its atomic weight is in parentheses at 247, simply because it's unstable and we can't really get a good number on that, on all the isotopes. Curium, it's a side note here. Obviously, it's named after Madame Curie, And I'm just curious, anybody know where Madame Curie, she won 2 Nobel Prizes, by the way. She was trained as a chemist. And in fact, her kids also won Nobel Prizes, smart family. Can anybody tell me where Madame Curie was from originally? A side note, history, chemistry history. Anybody know? Madame Curie. Yeah. Well, originally, a lot of people say she's from France, but it's not correct. Her husband was from France, who was her partner. And anyway, she originally was from Poland. And she went to France during that time period to get an education, because during that time, women were not allowed to get a higher education. So she went to France. France was the mecca of science at that time period, and got her doctorate. And her doctorate to this day is probably one of the best known doctorates, dissertations around. It's open to argument, but yeah, she did a lot. Anyway, what this does now is we're getting close to finishing this chapter here. All right, so after that, let's see, chemical formulas. We're going to briefly talk about chemical formulas, and then we're going to actually, down the road, not right now, we're going to learn how to put them together. All right. Now, keep in mind, the way we do this is we start with the elements, okay? Learn about the elements, learn about what they are, what as far as losing or gaining electrons, because once we learn that, that tells us how we can put them together to make compounds. And once we start putting compounds together, okay, then we can start reacting compounds and have chemical reactions and do calculations. But let's baby steps. All right, chemical formulas. What they tell us the type and the number of atoms present in the molecule, okay? Right now, they're not really telling you any type of bonding order. We're going to learn about that. Some of the bonding order is kind of understood, and I'll explain to you as we get there, okay? If a subscript is blank, it's understood like in mathematics that equal to 1. Okay, so we have here, for example, H2O. It says 2 hydrogens and 1 oxygen. Okay, so we have a total of 3 atoms in the molecule of H2O. Okay. Oh, by the way, we're talking about scientific names. You want to look up something kind of fun? Look up dihydrogen monoxide. Yeah, look that up on the internet. See what you come up with. It'll be interesting to see what you come up with. That, by the way, is the technical name for H2O, dihydrogen monoxide. Exactly. And you'll be surprised as to the hazards of dihydrogen monoxide. The way it's written, it's a chemical, so it must be bad. All right. Okay. So we got H2O, and right now, as I stated earlier, you might look at the H2O and think that the 2 hydrogens are bonded together, but they're not. We're always going to tell you what the central atom is. The way things are put together is we have a central atom, okay, which I'm just going to designate as A, okay, and then around it, we're going to have, I'm going to just designate as B. And sometimes you can have 4 Bs, sometimes you can have 2 Bs, 3 Bs, different, but you're always going to be told what the central atom is, and then everything else around it will be bonded, okay? All right, so for example, let's take this. This is a general formula. It doesn't designate the structure and how things are put together. But it's telling you C subscript 3, H subscript 6, O subscript 3, which tells you that there are 3 carbons, 6 hydrogens, and 3 oxygens in this compound, okay, whatever it may be, for a total of 12 atoms, okay? And that information you need to be able to identify, because here's what you hopefully know by now. You have a periodic table, correct? All right. You also know, there's a question. Oh no, not sugar. That could be acetic acid. Okay. Which sugar would have C6, H12O6, I believe. But the way it's written, it doesn't give you a specific formula. For example, and this is why I say this, is see, if you like vinegar, this is a little bit foreign right now, but 1, 2, 3, 4, 5, 6, 2 oxygens, 3 guys. This is vinegar. This is structure for vinegar, which would be that general formula. But I can rearrange these atoms to write totally different structures. Okay? And so right now our main goal here is to determine how many atoms of each we have for a particular compound. Okay? And here we got 3 hot carbons, 6 hydrogens, and 3 oxygens. Now, what you know now is on the periodic table, you know the atomic weight of each of these, right? You know that carbon is at 12.01. And you know there's 3 of them, so I can multiply 3 of them. Multiply 12.01 by 3, okay? And that gives you the total contribution of carbon for this molecule, regardless of what it is. Hydrogen, you know its atomic weight based on the periodic table of 1.0, and you know there's 6 of them. So you can 6 times 1.01. And oxygen, you know its atomic weight is 16.00, and there are 3 of them, okay? So total, you can add it up, you got 36.03, 6.06, and I got what, 48 here. All right, so 6.03, so I got 9, 0, I got 12, is that right, 12, and that's 20, okay, and 7, 8, 9. So 90.09 units grams per mole. Don't worry about the units. We're going to learn a lot about those units. But now we have the whole atomic weight for that molecule. And what even furthermore, I can take the contribution of each hydrogen, each atom. So I got 36.03 and divided by 90.09. Take the 6.03 divided by 90.09. Take the 48, divide that by 90.09. Multiply everybody by 100, and I get a percentage composition. And now I know the percentage composition for this particular compound, which is very unique for that compound. Okay, we're going to have some examples of that. But right now, the important part is you're going to find that a lot of times I throw in stuff that we're going to get to. So when we get to it, it's not as foreign. Okay, so I went a little bit extra here. That's okay. So we're going to learn how many atoms there are. We got 12 atoms here, okay, in this molecule. This one here, here's something to pick up on. You see a molecule, I see a compound, okay, formula given to you. This is, by the way, it's called ammonium carbonate, but that's not important right now. But you see a parentheses. Whenever you see a parentheses, what's in the parentheses is treated as a unit, which we don't separate. Why is that important? Because if you go to the periodic table, you're going to find examples of these units that we're going to utilize quite a bit right here. These are what we call polyatomic ions, a lot of these units. And whenever we need to add more than one unit, we don't separate the atoms. We keep them, that unit together, and we put a parentheses around it, and we put a subscript to designate that. In this example, we need 2 NH4 units, okay? And then so that means that there are 2 nitrogens, and guess what? 8 hydrogens total within the parentheses. We got 1 carbon and 3 oxygens, okay? For a total of 14 atoms. 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens, okay? So that's the takeaway from this particular exercise here. And that is to be able to determine how many atoms we have total and how many atoms we have individual with respect to individual elements. All right, because we're going to take this information and build on it, and then like I did the example of the percentage composition, we're going to use that. All right, so here we have, and here we'll call it a day after we're done with this last slide. We have H3PO4. What the compound is not important at this point, but I'll let you know what that is. It's H3PO4 is phosphoric acid, okay? I let you know now because it could come up in the nomenclature exam. You never know. And if you drink a lot of soda pop like me, you drink a lot of H3PO4, phosphoric acid. All right, well, it has 3 hydrogens, 1 phosphorus, and 4 oxygens for a total of 8 atoms, okay? Now here's another one. It's got a parentheses. Here's that unit inside of OH, a very specific unit, but there's 2 of them because look at outside the parentheses subscript. That means I got 2 of those units. So I got 1 calcium, 2 oxygens, and 2 hydrogens. And that's, by the way, is called calcium hydroxide. The next one is, its name is aluminum sulfate. Notice that there's no, I didn't put no prefixes. Now it's not calcium dihydroxide, it's just calcium hydroxide, okay? Aluminum sulfate, I didn't call it dialuminum trisulfate, no, aluminum sulfate. And why is that? Calcium is a metal. The OH is a nonmetal. Aluminum is a metal. The SO4 is a nonmetal. When I have a metal and a nonmetal together, no prefixes, just whatever they are. So it has 2 aluminums, 3 sulfurs, 12 oxygens, and that's a total of 17 atoms for aluminum sulfate. Okay. Oh, I guess I have one more slide. Sorry about that. The law of definite proportions. This basically says when H2O comes together, hydrogen, oxygen come together, they come together with 2 atoms of hydrogen and 1 of oxygen, which corresponds to 11.2% hydrogen and 88.8% oxygen. And that composition is true whether that water came from here in Arizona or in the other side of the world. It's still H2O, it's the same percentage, okay? Some of these percentage calculations are going to be done later, but it's the same principle I just talked to you about. Once I know the total atomic weight, I figure out the atomic weight of each of the atoms that play a factor in the compound and divide it by the total times 100, I get the percentage, okay? All right. That brings us to the end of chapter 4. And so I will post the end of this. And I will post these, chapter 3 and chapter 4. I should say load them, upload once I